Good evening. In the name of Allah, it is my pleasure today to introduce my lecture about gas laws, the practical approach. I would like to thank the organizing committee and to thank all attendees for their precious time. And I hope this will be beneficial for them. Okay. Our aim of the lecture, we will list each gas law and indicate the relevance to anesthetic practice, i.e. practical applications. So for each gas law, we will discuss three parameters: definition, equations, and the clinical application or practical application. Fluid, liquid, gas, and vapor, critical temperature, pressure, the Huggins-Poiseuille equation, STP, mole, Avogadro law, and number, Dalton law of partial pressure, basic gas laws like Poiseuille's law, Charles' law, Gay-Lussac law, then derived like combined gas law and universal gas law, gas laws of solubility, and gas laws of diffusion. About fluid, liquid, gas, and vapor, what is the difference between them? Fluid is a substance that is capable of flowing or moving. Okay? It may be liquid or gas and vapor. So, any substance can move or flow. It is a fluid like liquid or gas or vapor. Okay? The major difference between liquids and gases is compressibility. Liquid is incompressible, so if increased temperature, this will lead to dramatic increase in pressure. So we respect filling ratio during nitrous cylinder filling as it is liquid vapor cylinders due to its critical temperature and pressure. Okay. So if heat is added to the liquids, the molecules will gain kinetic energy to break what's called van der Waals forces between molecules to create a gas or vapor. Okay, so what's about critical temperature? Critical temperature, so far, each gas has its own critical temperature and critical pressure. It is the temperature above which and below which. Temperature above which the gas cannot be liquefied, whatever the pressure is applied. Temperature above which the gas cannot be liquefied, whatever the pressure is applied. Or temperature below which the vapor can be liquefied at its critical pressure. Why cannot be liquefied above the critical temperature? Because the molecules gain kinetic energy, so cannot be approximated to form the liquid. Okay. Another definition, or temperature at which gas must be cooled before it can be liquefied by pressure. So first cooling is important to liquefy gases, then apply what's called critical pressure. Okay, what's critical pressure? Critical pressure is the pressure needed to liquefy the gas at its critical temperature or vapor pressure of the substance at its critical temperature. Okay, so can we conclude the definition of vapor and gas? Vapor is a substance below its critical temperature. It's a substance below its critical temperature because it is related to a liquid, so we call it vapor below its critical temperature. While gas is a substance above its critical temperature. Separate identity, not related to a liquid, cannot be liquefied, so called gas. So to remember again, critical temperature above which gas, below which vapor, liquid. Next. What about Huggins-Poiseuille equation? Huggins-Poiseuille equation recognizes the laminar flow in Newtonian fluids. Describe the laminar flow, factors determining the laminar flow in Newtonian fluids. What's Newtonian fluids? Newtonian fluids, despite changes in flow rates or flow velocity, viscosity become constant. Constant viscosity despite the changes in flow rates or flow velocity. Okay. Huggins-Poiseuille equation describes that laminar flow in uniform tube diameter is directly proportional to the pressure difference and to the fourth power of radius. Okay. And inversely on viscosity and length. Then we can conclude the equation of resistance to flow. So by logic, resistance to flow is directly proportional to the length and viscosity and inverse proportion to the pressure difference and the fourth power of radius. What about practical application of Huggins-Poiseuille equation? About practical application of Huggins-Poiseuille equation, double pressure will double flow rate. But the most important, while double the radius, this will enclose through flow about 16 times. Okay, so why pore cannula better than central line to increase fluid flow? Why? Because we play on the fourth power radius. And why a 1 millimeter airway narrowing in a child with narrow airway already, whose airway may be only about 5 millimeter at the outset, results in such a drastic reduction in air flow. Okay, okay. What about STP? STP, what's called standard temperature and pressure. Standard temperature and pressure. Standard temperature at 0 Celsius, 273 Kelvin, or 32 Fahrenheit. And pressure about 1 bar, 101 kilopascal, about 760 millimeter mercury, about 14.6 pounds inch square. Why STP? Why standard temperature and pressure? A set of standard conditions have been chosen to make it easier to understand the gas laws and gas behavior. Okay, if we measure a gas volume, we must specify temperature and pressure. And also, at this standard condition, if we have 1 mole of gas, it will occupy 22.4 liter. 22.4 liter. Okay, but please respect the temperature units and respect the pressure units equivalent to each other in standard temperature and pressure. Okay, what about mole, Avogadro law, and number? What about mole, Avogadro law, and number? Mole definition, it is molecular weight in grams, as a mass. Molecular weight in grams. Mole contain Avogadro number equals 6.022 multiplied by 10 power 23. Or it is the amount of substance which contains particles in 15 and 12 grams of carbon-12. The most important to recognize that at STP, mole occupies 22.4 liter, and at room temperature, 20 degrees centigrade, it will occupy about 24 liters. This is the most important object. Okay. Let's recognize now that we must respect the fixed values of mole. Mole, molecular weight, certain volume, in certain temperature to get and or to solve any question or quiz. For example, if molecular weight of oxygen about 32 grams, 2 mole equal 32 grams, will occupy 22.4 liter at STP and occupy 24 liter at 20 degrees centigrade. Okay. Example, another example. What mass in 0.2 mole of isoflurane? What mass in 0.2 mole of isoflurane? Molecular weight of isoflurane equal 184 grams. So we can make it mole equal mass gram over molecular weight. So mass equal 0.2 multiplied by 184 equal 36.9 grams. So mass of 0.2 mole isoflurane is 36.9 grams. It's so easy. Okay. We can get now Avogadro number definition from mole definition. Okay. Number of particles in 12 grams of carbon-12. Number of particles in mole equals 6.022 multiplied by 10 power 23. So, how many molecules in 32 grams oxygen? Equal Avogadro number equals 6.22 multiplied by 10 power 23. Example 2. What volume of oxygen obtained from full cylinder at STP and the mass of 970 grams? Okay. As molecular weight of oxygen equals 32 grams, occupying 22.4 liter at STP, so 970 grams occupy what? We will multiply it to get 680 liters. How many mole and number of molecules in 11 grams nitrous? Okay. Molecular weight of nitrous contains Avogadro number 1 mole. Okay. So molecular weight of nitrous equal 44 grams. So 1 mole in 44 grams. How many moles in 11 grams? It will be equal 0.25 mole. So what number of molecules in 1 mole? It equals Avogadro number. So number of molecules in 0.25 mole equal, we will multiply 0.25 multiplied by the Avogadro number, which equal 6.02 multiplied by 10 power of 23. Okay. So what about Avogadro hypothesis? What about Avogadro hypothesis? At same temperature, equal volume of gases contain equal number of molecules. At same, equal. At same temperature, same pressure. For example, STP, equal volumes of gases will contain equal number of molecules like Avogadro number. But recognize that although equal volumes contain equal molecules, but the actual mass of different gases is different, because each gas have its own molecular weight. As oxygen, molecular weight equal 32 grams, and nitrous molecular weight equal 44 grams. So they are equal volume, contains equal number of molecules, but the mass of different gases is different. To continue about Avogadro hypothesis, equation P over N equal K. P, volume of gas. N, molar amount of the gas. K, constant. K. V1 over N1 equal V2 over N2. What is the practical application about Avogadro hypothesis? Calibration of vaporizer. Calibration of vaporizer. If 200 grams sevoflurane occupy 22.4 liter at STP, so what about 20 grams, 20 ml liquid? It will occupy 2.24 liters. So if 2.24 liters Sevos vaporized in vaporizer in 224 liter oxygen, so Sevo concentration will be 1%. Again, it is about how to change mass to volume. How to change mass to volume. Okay. Then sevoflurane concentration will be measured by a gas analyzer. Okay, to check this vaporizer calibration. So again, the most important practical application of Avogadro hypothesis is calibration of vaporizer. Okay, Dalton law of partial pressure. Remember partial pressure. So Dalton law of partial pressure states for a mixture of gases, the total pressure is always equal to the sum of the individual partial pressure. P total equal P gas 1 added to P gas 2. Okay, it's so simple, but let's go to the clinical or practical application. 1 and 2 about cylinder. The first and second clinical applications about the cylinders. At first, calculate the partial pressure of a gas in cylinder. How to calculate partial pressure of gas in a cylinder containing mixture of gases. Air cylinder with oxygen 20% and nitrous 80% with ambient pressure 100 kilopascal. So we will know the partial pressure of gas by multiplying the total pressure by the gas percent. So partial pressure of oxygen equal 100 multiplied by 20% equal 20 kilopascal, and partial pressure for nitrogen equal 100 multiplied by 80% equal 80 kilopascal. Then manufacturing cylinder producing 10% CO2 in oxygen mixture. Tell CO2, tell absolute pressure equal 13.80 bar. Then add oxygen to absolute pressure equal 138 bar. So overall percent of CO2 is 10%. Okay. Let's go to oxygen cascade. Oxygen cascade is an important practical application of Dalton law. Okay. We will calculate the atmospheric oxygen pressure. Then we will calculate the alveolar partial pressure of oxygen. So we will show that when we breathe normally about 21 kilopascal oxygen, it becomes only 14.9 by the time it reaches the depths of our lung. This practical application of Dalton law is the alveolar gas equation. So how can we calculate the atmospheric oxygen pressure? We will multiply the inspired oxygen concentration by atmospheric pressure, then 0.21 multiplied by 101, it will be equal 21.2 kilopascal. And alveolar gas concentration will be the alveolar CO2 equal fractional inspired oxygen multiplied by the difference between the total pressure minus the saturated vapor pressure in the alveoli, then to be subtracted from the alveolar CO2. Okay. Take care, we can calculate the partial pressure of oxygen using kilopascal units and also by millimeter mercury units in some reference and in some reference. Okay, so again, we must remember that alveolar gas equation may equal alveolar partial pressure of oxygen equal inspired oxygen concentration multiplied by the difference between the atmospheric pressure to the saturated vapor pressure in the alveoli, then divided by the ratio between the CO2 in the alveoli and the respiratory, what's called respiratory gas quotient, 0.8. Okay? Okay. Gas laws. Okay. The gas laws describe the relationship between pressure, volume, and temperature of gases. If one constant, the other will be variable. Okay. Typically, the ideal gas laws are referenced relative to standard temperature and pressure. Okay. As we said, 273 Kelvin, 0 Celsius, and atmospheric pressure at sea level 101 kilopascal or 760 millimeter mercury. Don't forget absolute pressure and absolute temperature by Kelvin. And all gases in cylinder will respect gas laws and universal gas laws except nitrous and may also CO2 cylinder because below its critical temperature they will contain liquid vapor. Remember that CO2 as same as nitrous for their critical temperature and critical pressure. So also CO2 cylinder below its critical temperature will contain liquid and vapor. So all gases in cylinder will respect gas laws and universal gas laws except nitrous and CO2 below its critical temperature. Boyle's law. Although boiling, but temperature constant. Although boiling, but the temperature constant. So at constant temperature, the absolute pressure of a gas is inverse proportion to the volume. PV equal constant, or P multiplied by V equal constant, or pressure multiplied by volume equal constant. P1 V1 equal P2 V2. And again, remember in Boyle's law that absolute pressure will equal gauge pressure added to atmospheric pressure. Practical application of Boyle's law will be about 4 practical applications. The most important is the fourth one. Okay. Let's move to the lung mechanics. Chest expansion with increased volume respiration will make negative intrathoracic pressure, allow air entry during respiration. Then hyperbaric oxygen therapy will increase pressure. That will make decrease the volume of endotracheal cuff, so make an air leak. So to prevent air leak, we must fill it with saline. Okay. At constant temperature, we can calculate the change in volume of pneumothorax size with change in pressure. 1,500 ml volume pneumothorax at sea level at 101 kilopascal. Then if the patient travel and ascend in a plane, what is the new volume at 90 kilopascal? The answer will be V2 equal V1 V1 over V2 and will be equal 1060 liters, 600 liters. Okay, so we can say that at high altitude, low pressure, pneumothorax size will expand. That may cause tension in the thorax, give us a tension that may need tracheostomy or drainage of this air collection. Okay, the most important clinical practical application, policy number 4. Teach you how to know the amount of oxygen available from its cylinder to be used in atmospheric pressure. Okay, you are about to transfer a patient who is requiring 15 liters of oxygen. You have a full 10 liter oxygen cylinder size F with a gauge pressure of 137 bar. How long will the oxygen cylinder last? Okay, 3 steps to solve this quiz. Number 1, calculation of the absolute pressure in the cylinder. P total equal P atmospheric added to P gauge, atmospheric pressure added to gauge pressure will be equal about 13,800 kilopascal. Then V1 V1 equal V2 V2. So we'll get the new volume about 1,380 liters. This gives us the final volume, which at a fresh gas flow about 15 liters per minute will last about 90 minutes. About 90 minutes. This is an important example. Let's move to Charles' law or second gas law. Remember, Charles' convection filter. Remember, Charles convection Kelvin. Okay. At constant pressure, the volume of gas is proportional to absolute temperature. Okay. At constant pressure, the volume of gas expands by 1 over 273 of its original volume for every 1 degree rise in temperature and vice versa. Okay. Let's now remember an information about nitrous. As nitrous diffuse in our body cavities, it will increase a volume of compliant spaces like intestine and will increase the pressure of non-compliant spaces like middle ear. Okay, the same in second gas law and third gas law. In second gas law, increased temperature with increased volume in gases with compliant spaces, while increased temperature will increase pressure in non-compliant spaces like cylinders. Okay, so let's move to the clinical applications of Charles law, second gas law, convection Kelvin. What about 0 Kelvin or true zero? Cooling of gas till 0 Kelvin, the gas volume will be 0, and at this point, the gas liquefies. That means that absolute 0 Kelvin, no volume of gases. So we call this Kelvin absolute 0 Kelvin because the gas will be absolute and all gas will be turned to a liquid, all gas will be liquefied. Okay. Convection currents, convection mechanism of a heat loss. Warmed air layer adjacent to body surface expand, become less dense, and rise away from the patient, make heat loss. Okay, so convection currents carry heat away from patient, making what's called dynamic heat loss. What about Gay-Lussac law, third gas law? At constant volume, absolute pressure of gas is proportional to the absolute temperature. Okay, P proportional to T, while the volume is constant. For each degree change in temperature, gas pressure will be changed by 1 over 273 of its original pressure. The most important application for cylinders. Why? Because cylinders are non-compliant spaces. Practical application of Gay-Lussac law, third gas law. For cylinders, double temperature, cylinder dropped in fire, double pressure, danger of explosion. Okay. Example, oxygen cylinder of 137 bar dropped in fire. If double temperature, double pressure to 137 multiplied by 2 equal 274 bars and explosion. Okay. Nitrous cylinder at higher risk of explosion than oxygen cylinder. Again, because nitrous cylinder contains liquid vapor and liquid is incompressible. We can give another information about this fullerene vaporizer. Thick combustion this fullerene vaporizer by electric heater may show double temperature, double pressure. Why? Because double temperature by electric heater make the saturated vapor pressure will be doubled again. So what about combined gas law? Combined gas law, the three are variables. The pressure and volume and temperature are variables. Okay, so P1 over T1 equal P2 V2 over T3. This is an example that we can put the fixed values to know the variable which is V2. Rearranging the combined gas over V2, then we'll gain 3.5 liter of gas in the new temperature and pressure. But remember that at standard temperature and pressure, we will put the pressure by 760 and the temperature by the Kelvin. But we respect the absolute temperature and absolute pressure. Okay? Okay. The most important example here is to respect expression of temperature by Kelvin. Okay? Okay. Universal gas law, PV equal nRT. PV equal nRT. P volume, P pressure, P temperature by Kelvin are universal gas constants. Universal gas constant equal 8.3 by certain term and or 0.8 by certain term. Okay. If n equal number of moles in a gas for 1 mole, PV will equal RT. pressure multiplied by volume will equal the constant multiplied by temperature. What is the clinical application? Clinical application, number one, pressure gauge. Pressure gauge will express the contained state of gas cylinder, only oxygen. Why? Because B is proportional to the M, as R and T and V are constant. So the oxygen pressure gauge indicates its volume. While nitrous liquid gas cylinder, pressure gauge doesn't indicate its volume. Okay. How to calculate that 1 mole as 32 gram oxygen at STP will occupy 22.4 liters using universal gas law? Okay, PV equal nRT, then 1 mole PV equal RT. So we can calculate the new volume at STP will be equal to 22.4 liters. Okay. Now we will compare between the oxygen and nitrous cylinder as an important application of gas laws on cylinders. Okay. At first, oxygen cylinder only gas at room temperature due to its critical temperature and critical pressure. At room temperature, 20 degrees centigrade, it will be above oxygen critical temperature, which equal minus 120 degrees centigrade. So sure, it will be gaseous. But for nitrous cylinder will be liquid vapor at room temperature due to its critical temperature and critical pressure. As at room temperature, 20 degrees centigrade, below nitrous critical temperature, 36 degrees centigrade, sure it will be liquid or vapor. Then applies Boyle law, B1 equal B2 V2, no volume of oxygen cylinder at high pressure. Cannot apply law in nitrous cylinder. We can apply second and third gas law, cannot apply second and third gas law. Then apply universal gas law, PV equal nRT, while TV are constant, so P proportional to N. So reduction in gas pressure in oxygen cylinder make reduction in cylinder content. For example, full E oxygen cylinder at pressure 137 bar at 2000 pound S square will contain about 625 liters. So if pressure gauge reads 65 bar equal 1000 pound each square, so the cylinder will contain half. So we will divide 625 over 2 equal 312 liters. We cannot apply universal gas law in nitrous cylinder, so let's revise nitrous cylinder. Heat pressure equal 50 bar. Then we'll continue to read 50 bars equal 750 pound square. Even cylinder begin to empty as liquid vaporized to replace vapor. So pressure gauge is not accurate to know nitrous amount. So the most important to better weight cylinder. Let's move to some examples and quiz about oxygen cylinder and nitrous cylinder. Example 2. The oxygen cylinder reads 90 bars. How 90 bar? How long delivered oxygen will be from the cylinder at rate of 9 liters per minute. Okay, 137 bar at 625 liters. Send the new pressure 90 bar. What equal liter? So the new volume will be 410 liters. Then divided to 8 liters per minute equal 50 minutes. We return again to the physical characters of nitrous cylinder. There are 6 important physical characters of nitrous cylinder. Number 5, filling ratio. Why make nitrous cylinder partially filled? As if completely filled with increased ambient temperature, increased pressure make explosion as the liquid is incompressible than gas. What is filling ratio? Filling ratio equal weight of liquid nitrous in cylinder over weight of water required to fill the cylinder. For nitrous and CO2, filling ratio is 0.75 in hot climate and lower ratio 0.67 in normal climate. Why ice frost formation at cylinder gauge? Due to latent heat of vaporization of liquid nitrous in the cylinder, so temperature drop and ice formation at the cylinder gauge. Okay, what examples of nitrous again? for calculation of the amount of gas in a cylinder with known mass at STP and room temperature. Okay, mass and volume. So we can apply the idea about mole, molecular weight, certain volume, and certain temperature. Okay, we will calculate it at STP and at room temperature. A, if a typical full nitrous cylinder contains 3.4 kilograms of nitrous, what volume of nitrous is obtained from this cylinder? The molecular weight of nitrous is 44, so 1 mole, 44 grams of nitrous will occupy 22.4 liters of nitrous vapor at STP. Therefore, 3,040 400 grams of nitrous will occupy X liters of nitrous vapor at STP. So the new volume will be about 1,730 liters of nitrous vapor at STP. The same will be applied, but recognize that at room temperature, we will make the temperature by 20 degrees centigrade. Another example for nitrous, each cylinder contains liquid nitrous, shows 750 pound inches square, 50 bar. When it's full and it will contain 1,600 liters, 1,600 liters. Then continue to read 750 pound inches square till 3/4 of nitrous has left cylinder. So when nitrous cylinder begins to fall from its 750 pound inches square, how many liters remain in the cylinder? The answer, we will multiply 1,600 to the 25% equal 400 liters. So we can say that when the pressure gauge of a nitrous cylinder reaches 700 pound inches square less than 750 pound inches square, its volume will be 25 of its original volume. Gas laws of solubility, Henry's law. At particular temperature, the amount of gas dissolved in a liquid is proportional to the partial pressure in equilibrium with the liquid. Okay. Practical application, decompression sickness or gas embolism. Nitrogen will come out of solution blood as small bubbles. Gas embolism if diver ascend abruptly. So as low pressure, the solubility of nitrogen in blood will decrease. So it will form a gas bubble, gas embolism, decompression sickness. Then what about hyperbaric oxygen therapy? When patient exposed to free pressure atmosphere, this will increase the dissolved oxygen concentration dramatically 3 times. Okay, we can move to the next slide for more information. Okay, for example, about the hyperbaric oxygen. Oxygen solubility coefficient will equal 0.003 ml per deciliter. Then by application of alveolar gas equation to get partial pressure of oxygen to be multiplied by solubility coefficient. Okay. So at room temperature, the dissolved oxygen content will be 0.26 ml per deciliter. And if the patient breathes 100% oxygen, it will increase to 1.7 ml per deciliter. And at 3 atmosphere hyperbaric, the dissolved oxygen will increase to 5.6 ml per deciliter 3 times. This is the equation that we can collect from in this table, PO2. Then we will gain the alveolar O2. Then we multiply the solubility coefficient to get the dissolved oxygen. To get that at atmospheric, 3 atmosphere, the dissolved oxygen will be raised 3 times to get 5.6 ml per deciliter. Okay. So what about gas laws of diffusion? Fixed law of diffusion. Fixed law states that the rate of diffusion of substance across unit area, such as a surface or membrane, is proportional to the concentration gradient. Fixed law applies only in a single homogeneous phase, and a slight modification is needed if gases is transferred from one phase into another, as in the case of gases passing into solution. So we have a gaseous phase and liquid phase. What's called modified fixed law. The modified form of the law, modified fixed law, is that the rate of diffusion of a gas across a membrane or surface area is proportional to what's called tension gradient or pressure gradient. Okay. So what's about Graham's law? Graham's law of diffusion states that the rate at which the gas diffuses is inversely proportional to the square root of its molecular weight. The larger the atom or molecule, the slower it diffuses. So the rate of diffusion will proportional to the inverse proportion to the square root of the molecular weight. The larger the molecules, the slower the diffusion. Okay. What about the practical application of gas laws of diffusion? Number one, what's called gas flux. Gas flux is the amount of gas which passes through a membrane like alveolar membrane per unit of time. Gas flux will be A over T multiplied by D multiplied by the pressure difference. Okay, so where A surface area for diffusion, and then T the thickness of membrane, B partial pressure of the gas in either side of the membrane. So the term D is the diffusion coefficient. And this is where Graham's law features, because the D is proportional to the solubility of the gas divided by the square root of the molecular weight. So the next example about the diffusion capacity of CO2 for CO2 is 20 times that of oxygen. As CO2 is 20 times soluble that oxygen, although molecular weight of oxygen 32 and for CO2 is 44 grams. So in pulmonary edema with limited diffusion capacity, hypoxemia and hypoxia will occur likely and earlier than hyperthermia. Okay. The next slide, the last slide, try to solve this quiz about the oxygen cylinder reading 1,000 pounds square. Then how long would be able to run this cylinder at fresh gas flow rate about 10 liters per minute? The answer will be 30 minutes. Thank you for good listening. Have a nice time.